These are the notes for, or at least the start of the notes for chapters 1 and 2 in one-dimensional motion, dealing with displacement, velocity, and acceleration. So the first thing to talk about is how we might picture motion, and sometimes these are called motion maps or motion diagrams. But the idea here is that if we take a picture of something in equally spaced time intervals, that we can see that this guy here is, and oops, we can see that this guy here is equally spaced. And so what that means is if I'm taking those pictures equal time intervals, that he's moving the same distance in the same amount of time. So he's moving a constant rate. And it's hard to draw the guy with the Olympic torch all the time, so we can assume, do what's called a particle model and assume the object is a dot. And we can see the dots there below are equally spaced, and therefore moving object is moving at with constant motion. If the dots were to get farther apart, that would mean the object is speeding up, and if they are getting closer together, it would indicate the object is slowing down. So this is just a question dealing with which car is moving faster, car A or car B. Again, knowing that the pictures there are taken at equal time intervals. Clearly car B is farther apart and therefore is going faster. It's traveling farther distance in the same amount of time. This one, if you look at the dots, this is an object that is going down. But you can see that the dots are getting farther apart. And so here you have a rock drop from the roof of a building. And then we need to talk about the difference with some terminology here. So I have 3 words that are often used interchangeably, even though they have some subtle differences, subtle and important differences. Distance is just how far you have gone. So it would be measured in miles or feet or inches or centimeters or meters. Position is basically where you're at. It's your coordinates. And displacement, which is the term we most often need to use, is your change in position. So it's kind of an as the crow flies, or you might say it's how far you are from where you started. And so a couple questions dealing with that. John gets on the interstate at exit 130. He turns around at exit 145 and comes back to 140. What distance did he travel? So he went from 130 to 145, that's 15 miles, and then came back another 5 miles to get to his exit. So he traveled a total of 20 miles. But the second follow-up question to that is, what is his displacement? He started at exit 130, he ended at exit 140, therefore his displacement is only 10 miles. Speed and velocity, again, are 2 terms that are often used interchangeably. There are subtle but important differences between these. So speed is how fast you move. We have any distance over time units. The common one we're used to is miles per hour. The standard for science is meters per second. We can also talk about an instantaneous speed versus an average speed. Instantaneous is how fast you're moving now, versus average, which is how fast you have gone over an entire trip. And those are different, or can be very different. For example, if I travel from Fargo to Lincoln, Nebraska, my average, it's 450 miles, my average might be 65 miles per hour for the whole trip. But at any one moment, like if I'm traveling through South Dakota, speed limit is 80 miles per hour. I could be going 80 miles per hour. I could hit a construction zone and only be going 50 miles per hour. I could be stopped to get a snack and my velocity would be 0, or speed would be 0. And speed does not need any kind of a direction. Velocity is very similar, but the biggest difference is it needs a direction. And so we call it a vector. And we have certain directions that are considered negative. And so those directions that would be considered negative would be the southwest, down, left, and backwards. We still can talk about instantaneous versus average, but what we typically calculate is an average velocity. And here's your first equation. I often will put it in terms of d equals v average t. And it's very important to remember that this is the average velocity. It's not a final velocity, it's the average over the entire time that you have been moving. So a couple other questions. These are true-false statements. A car traveling with constant speed must have a constant velocity. That is not true, because a constant velocity means both the speed and the direction are the same. So constant speed, I could be changing my direction. I might not be, I might be. But if I flip that around, a car traveling with a constant velocity must have a constant speed. That is true, because a constant velocity means both the speed and the direction are staying the same. So we have we have an example here. In 2009, we had a swimmer who reportedly swam 2,100 miles from Africa to the Caribbean in 27 days. Calculate her speed in miles per hour and meters per second, and compare this to Michael Phelps. So if we assume that she has, let's just say she swam 10 hours a day. So she was doing, oops, I need to back it up and get a pen. Oops. There we go. Okay, let's assume she swam 10 hours a day. So she spent 270 hours in the water. So if I figure out her speed at 2,100 divided by 270 and run those numbers, I get basically 7.8 miles per hour. I'm going to put miles on the top here, 7.8. Okay, I'm going to convert that to meters per second here. So I've got 1 mile is 1610 meters, and 1 hour is 3,600 seconds. So if I take my 7.8 and multiply it by 1610 and divide it by 3,600, I get 3.5 meters per second. So let's compare that to Mr. Phelps, who did, and we can just do meters per second here, but he did 200 meters, and his time here, if I add 60 seconds to 54, I get 114 seconds. 200 divided by 114 gives me 1.75. So essentially the fastest swimmer in the world, over 200 meters, could only go this fast. And she's claiming that over 27 days, 10 hours a day, she went this fast. So as soon as the story came out, it was published all over the news, but somebody realized there's something wrong here, and she had to retract her story. She finally admitted that the boat was moving even when she was sleeping, probably way faster than her swimming. And so physics won the day. All right, and the last topic we're going to talk about here, and then we'll finish the notes in class, is acceleration. The symbol for acceleration is a little a. It's a change in velocity. So if your velocity changes, then you are accelerating. Average acceleration is what we're going to be dealing with. It's just the total change in velocity over some period of time. And it's calculated this way. And there are 3 equations that are used. I'm trying to get the pen. It's not. There we go. Pen. Okay. Right here, this is the definition of acceleration. It's the change in velocity, final minus original velocity, divided by the time. We can rearrange it, and then we have 2 other equations that have acceleration in it. And these 3 equations, cumulatively, are called the kinematic equations. And they are used, we'll be using these all year. So you want to kind of become familiar with all of these. And they just require different pieces of information to solve for different parts. So here's a question. Velocity of a ball down a ramp is indicated in the table. So clearly the velocity increases, but we want to know what happens to the acceleration. So on this one, if we take a look at the acceleration here, right here, you can see that the velocity is increasing, but it's increasing by the same amount every second. It's increasing by 3. It goes from 2 to 5 to 8 to 11 to 14. So the amount it's increasing per time, again, that's the definition of acceleration, is the same. It stays constant. So the correct answer here is B. And then just like velocity could be negative if it was in a negative direction, acceleration can also be negative. It has a direction. But how you determine whether the acceleration is positive or negative will depend on two things. It depends not only on the direction, but it also depends on whether the object is speeding up or slowing down. So it's like you assign the direction a positive or negative value. You assign speeding up a positive and slowing down a negative. If you have a combination of two positives or two negatives, your acceleration is positive. If you have a positive with a negative, your acceleration is negative. So examples, if we have north slowing down, I'm going to get my pen back. Okay, so I have my pen. North slowing down. North would be a positive direction, with slowing down is negative, and so the combination would be a negative acceleration. And if I do south slowing down, I have a negative. I have another negative. I keep losing my pen. Actually, so I'm going to get this last one up here and then we'll do the pen. So south slowing down would be a negative. Triple with technology. All right, so we had north slowing down. We already did that one. South is negative, slowing down is negative, and so the combination here is going to be a positive acceleration. West is negative, speeding up is positive, the combination is negative acceleration. East is positive, speeding up is positive, and that gives me a positive acceleration. And then just the last one again, north was positive, slowing down was negative, and that combination is negative. So if we have a positive acceleration and it's slowing down, what direction is its velocity? So positive acceleration means I either had to have two positives or I had to have two negatives. So if it's slowing down, that's negative. That means the direction also has to be negative. And the only option here is south. And then the last but not least, we have this example. Jaguar accelerates from rest. And all right, so how far does the car move? So I know the A, I know the time, I know the initial velocity. So I know VODT, VOA and T, and I'm looking for D. So I'm going to use the D equals VOT plus 1/2 AT squared. The VO here is 0, so I can eliminate that. And so if I plug the numbers in of 6.1 and 7 and square the 7, I end up with 149.5. And so we will continue these notes in class.